In this lecture, we're going to continue with the theme of building abstractions. Thus far, we've focused entirely on procedural abstractions, the idea of capturing a common pattern of a computation within a procedure and isolating the details of that computation from the use of the concept within some other computation. Today, we're going to turn to a complementary issue, namely how to group together pieces of information or data into abstract structures. We will see that the same general theme holds. We can isolate the details of how the data are glued together from the use of the aggregate data structure as a primitive element in some computation. We will also see that the procedures we use to manipulate the elements of a data structure often have an inherent structure that mimics the data structure. And we will use this idea to help us design our abstractions and their associated procedures. Let's review what we've been looking at so far in the course. In particular, the idea of using procedural abstraction to capture ideas. The game here was to take a common pattern of computation, capture that by formalizing it with a set of parameters that capture the parts that vary, and putting that inside a procedure so that that whole process becomes the body of a new procedure. Once we have that procedure, we give it a name so that we can refer to it, and then we can use that procedure as if it's a primitive, just using its name and hiding the implementation details from the user who simply wants to use the method and not know what's inside of it. This means we can treat the procedure as if it's a kind of black box. We need to provide it with inputs of a particular type. We know by the contract associated with the procedure that if we do apply appropriate inputs to it, we'll get out an output of a particular type that satisfies the contract of what the procedure is computing. And by giving the whole procedure a name, we create this black box abstraction in which we use the procedure without knowing any of the details inside. Or in particular, the details of how the contract is enforced that maps inputs to outputs is buried within the procedure and is not of any interest to the user who simply wants to make sure he can use inputs to get to outputs of the appropriate type. So let's use this idea to look at a more interesting algorithm than the earlier ones we've examined. Here again is Heron of Alexandria's algorithm for computing good approximations to the square root of a positive number. Read the steps carefully as we're about to implement them. Now, let's use the tools we've seen so far to implement this method. Notice how the first procedure uses the ideas of wishful thinking and recursive procedures to capture the basic element of Heron's method. Try is a procedure that takes a current guess and the x and captures the top-level idea of the method. It checks to see if the guess is sufficient. If it is, it simply returns the value of that guess. If it is not, then it tries again with a new guess. Note how we were using wishful thinking to reduce the problem to another version of the same problem, and to abstract out the idea of both getting a new guess and checking for how good the guess is. These are procedures we can subsequently write, for example, as shown. Finally, notice how the recursive call to try will use a different argument for guess, since we will evaluate the expression before substituting into the body. Also notice the recursive structure of try and the use of the special form if to control the evolution of this procedure. The method for improve simply incorporates the ideas from the algorithm, again with a procedure abstraction to separate out the idea of averaging from the procedure for improving the guess. And finally, notice how we can build a square root procedure on top of the procedure for try. If we think of each of these procedures as its own black box abstraction, then we can visualize the universe containing these procedures as shown. Each procedure exists with its own contract, but each is accessible to the user simply by referring to it by name. While this sounds fine in principle, there's a problem with this viewpoint. Some of these procedures are general methods, such as average and square root, and should be accessible to the user, who might utilize them elsewhere. Some of them, however, such as try or good enough, are really specific to the computation for square roots. Ideally, we would like to capture those procedures in a way such that they can only be used by square root and not by other methods. Abstractly, this is what we'd like to do. We would like to move the abstractions for the special purpose procedures inside of the abstraction for squirt, so that only it can use them, while leaving more generally useful procedures available to the user. In this way, these internal procedures should become part of the implementation details for squirt, but be invisible to outside users. And here's how to do this. Note that the definition of squirt binds this name to a lambda. Within the bounds of that lambda, we have moved the definitions for improve, good enough, and squirt iter, which is what we've renamed try. By moving these procedures inside the body of the lambda, they become internal procedures, accessible only to other expressions within the body of that lambda. That is, if we try to refer to one of these names when interacting with the evaluator, we will get an unbound variable error. But these names can be referenced by expressions that exist within the scope of this lambda. The rules of evaluation say that when we apply squirt to some argument, the body of this lambda will be evaluated. At that point, the internal procedures and the internal definitions are evaluated. The final expression of the lambda is the expression squirt iter 1.0, which means when squirt is applied to some argument by the substitution model, it will reduce to evaluating this expression, meaning it will begin the recursive evaluation of guesses for the square root. In fact, we can stress this by drawing a box around the boundary of the outermost lambda. Clearly that boundary exactly scopes the black box abstraction that I wanted. This is called block structure, and you can find out a lot more about this by reading in the textbook. Schematically, this means that squirt contains within it only those internal procedures that belong to it, and behaves according to the contract expected by the user, without the user knowing how those procedures accomplish this contract. This provides another method for abstracting ideas and isolating them from other abstractions. So in summary, we've been using procedural abstractions as ways of isolating details of a process from its use, and letting the designer decide both which ideas to isolate and the order in which to do them in order to support general patterns of computation. One of the lessons you should be learning is that good planning is often involved in deciding how to collect the procedures together so that we make new things easier to do. So let's take that idea of abstraction and build on it. To set the stage for what we're about to do, it's useful to think about how the language elements can be grouped together into a hierarchy. At the atomic level, we have a set of primitives. In Scheme, these include primitive data objects, numbers, strings, and booleans, and these include built-in or primitive procedures. For numbers, things like times, plus, equal, greater than. For strings, things like string equals substring. For booleans, things like and, or, not. To put these primitive elements together into more interesting expressions, we have a means of combination. That is, a way of combining simpler pieces into expressions that can themselves be treated as elements of other expressions. The most common one, and the one that we've seen in the previous lectures, is procedure application. This is the idea of creating a combination of sub-expressions nested within a pair of parentheses. The value of the first sub-expression is a procedure, and the expression captures the idea of applying that procedure to the values of the other expressions, which means, as we have seen, that we can substitute the values of the arguments for the corresponding parameters in the body of the procedure and proceed with the evaluation. We know that these combinations can themselves be included within other combinations, and the same rules of evaluation will recursively govern the computation. Finally, our language has a means of abstraction, a way of capturing computational elements and treating them as if they were primitives, or said another way, a method of isolating the details of a computation from the use of a computation. Our first means of abstraction was define, the ability to give a name to an element, so that we could just use the name, thereby suppressing the details from the use of the object. This ability to give a name to something is most valuable when used with our second means of abstraction, capturing a computation within a procedure. This means of abstraction dealt with the idea that a common pattern of computation can be generalized into a single procedure, which covered every possible application of that idea to an appropriate value. When coupled with the ability to give a name to that procedure, we engendered the ability to create an important cycle in our language. We can now create procedures, name them, and thus treat them as if they were themselves primitive elements of the language. The whole goal of a high-level language is to allow us to suppress unnecessary detail in this manner, while focusing on the use of a procedure abstraction to support some more complex computational design. Today, we're going to generalize the idea of abstractions to include those that focus on data rather than procedures. So we're going to talk about how to create compound data objects, and we're going to examine standard procedures associated with the manipulation of those data structures. We'll see that data abstractions mirror many of the properties of procedural abstractions, and we will thus generalize the ideas of compound data into data abstractions to complement our procedural abstractions. So far, almost everything we've seen in Scheme has revolved around numbers and computations associated with numbers. This has been partly deliberate on our part, because we wanted to focus on the ideas of procedural abstraction without getting bogged down in other details. There are, however, clearly problems in which it is easier to think in terms of other elements than just numbers, and in which those elements have pieces that need to be glued together and pulled apart while preserving the concept of a larger unit. So our goal is to create a method for taking primitive data elements, gluing them together, and then treating the result as if it were itself a primitive element. Of course, we'll need a way of degluing the units to get back to constituent parts. What do we mean when we say we want to treat the result of gluing elements together as a primitive data element? Basically, we want the same properties we had with numbers. We can apply procedures to them, we can use procedures to generate new versions of them, and we can create expressions that include them as simpler elements. The most important point when we glue things together is to actually have a contract associated with that process. That is, we don't care about the details of how things are glued together and unglued, if you like. What we care about is the contract that says the two mechanisms work hand in hand, so that no matter how we put them together, we're guaranteed when we use the right piece to unglue that we get back out what we started with. And ideally, we'd like this process of gluing things together into compound data to have the property of closure. And what closure means is that we can take the result of whatever we did when we created a compound data object and treat that thing itself as if it's a primitive, so that it can be, for example, the input to another operation of creating a compound data object. We'll see that not all methods for creating compound data have this property, but the best and most powerful of them do. They are closed under the operation of creation of the data structure, and the results of any one of those things can be used as a primitive anywhere we want. Scheme's basic means for gluing things together is called cons, short for constructor, and virtually all other methods for creating compound data objects are based on cons. Cons is a procedure that takes two expressions as input. It evaluates each in turn, and then glues these values together into something called a pair. Note that the actual pair object is the value returned by evaluating cons. The two parts of a cons pair are called the car and the cdr. And if we apply the procedures of those names to a pair, we get back the value of the argument that was evaluated when the pair was created. Note that there's a contract here between const, car, and cdr, in which const glues things together in some arbitrary manner, and all that matters is when car, for example, is applied to that object, it gets back out what we started with. Note that we can treat a pair as a unit. That is, having built a pair, we can treat it as a primitive and use it anywhere we might want to use any other structure. So we can pass a pair in as an argument to some other data abstraction. We can return a pair as a value from some data abstraction. In this way, we can create elements that naturally can be thought of as units, which happen themselves to have components within that are also naturally thought of as being units. So we can build up levels of hierarchy of data abstractions. For example, suppose we want to build a little system to reason about figures drawn in the plane. Those figures might be composed of points in the plane, which we can easily build using a constructor. Given an x and y coordinate, we make a point, and we have, of course, things that get back out the pieces, building on top of car and cdr. Notice, by the way, there's a nice little contract between makePoint as the constructor and pointX and pointY as the selectors. Because they're built on top of const, car, and cdr, they inherit the abstraction contract of those things, which means that however I glue things together with makePoint, pointX will get back out the right piece. Now, if I want to draw line segments in the plane, they have 2 points, an end point and a start point, so I can build a segment by simply gluing together 2 points, which notice themselves may also be things glued together using cons. And of course, I'll have selectors for getting back out pieces, like the start point of the segment is the first element of that segment, and it itself is a pair that's returned. So the point is that const pairs have this property of closure. I can glue things together, create an abstraction, treat them as a single unit, and use them to be glued together into higher order structures without any problem. We can formalize what we've just seen in terms of the abstraction of a pair. This abstraction has several standard parts. First, it has a constructor for making instances of the abstraction. The constructor has a kind of contract in which objects A and B are glued together to construct a new object, called a pair, with 2 pieces inside. Second, it has some selectors or accessors to get the pieces back out. Notice how the contract specifies the interaction between the constructor and the selectors. Whatever is put together can be pulled back apart using the appropriate selector. Typically, a data abstraction will also have a predicate, here called pair question mark. Its role is to take in any object and return true if the object is of type pair, something constructed by const. This allows us to test objects for their type, so that we know whether to apply a particular selector to that object. A key issue here is the contract between the constructor and the selectors. The details of how a constructor puts things together are not at issue, so long as, however the pieces are glued together, they can be separated back out into the original parts by the selectors. So here's that idea stated one more time. There's a contract between the constructor and the selectors. Car of a const of something gives us back out that thing. Cdr of a const of something gives us back out that thing. It pulls out the right pieces. The contract just says they work together. The details of how it's done shouldn't matter to the user of this data abstraction. Also again, notice how pairs have that nice property of closure. We can use the result of a pair as the element of any new pair to const things together in arbitrary form and arbitrary structure. So, how do we use the idea of pairs to help us in creating computational entities? To illustrate this, let's stick with our example of points and segments. Suppose we construct a couple of points using the appropriate constructor, and we then glue these points together into a segment. Now suppose we want to think about the operation of stretching a point. That is, pulling or pushing a point along a line from the origin through that point. Ideally, we would just think about this in terms of operations on elements of a point, without worrying about how the point is actually implemented. We do this with the code shown. Note how this code creates a new data object. If we stretch point P1, we get a new point. Also note, as an aside, how a const pair prints out with an open and closed parenthesis, and with the value of the two parts within those parentheses separated by a dot. Thus, the point created by applying our stretch procedure has a different value for the x and y parts than the original point, which is still hanging around. As we might expect from the actual code, we get out the values of the parts of P1, but then make a new data object with scaled versions of those values as the parts. And we can generalize this idea to handle operations on segments as well as points. Note how each of these procedures builds on constructors and selectors for the appropriate data structure, so that in examining the code we have no sense of the underlying implementation. These structures happen to be built out of const pairs, but from the perspective of the code designer, we rely only on the contract for constructors and selectors for points and segments. Now, suppose we decide that we want to take a group of points and manipulate that group in some way. For example, a figure might be defined as a group of ordered points, with segments between each consecutive pair of points. And we might want to stretch that whole group, or rotate it, or do something else to it. How do we group these things together? Well, one possibility is just to use a bunch of const pairs, for example, such as shown here. But while this is a perfectly reasonable way to glue things together, it's going to be a real bear to manipulate. Suppose we want to stretch all these points. We would have to write code that would put together exactly the right collections of cars and cooters to get out the pieces, perform a computation on them, and then glue them back together again. This will be a royal pain. It would be much better if we had a more convenient and conventional way of gluing groups of things together, and fortunately we do. So pairs are a primitive way of gluing two things together. This is nice when I just have two things, but of course life doesn't just come in pairs. I may also want to be able to glue things together that come in arbitrary numbers of units, and I need a way of doing that in a convenient form. Fortunately, Scheme has such a basis for us, another way of gluing things together that is a more conventional interface into structures, and that form is called a list. So a list is a data object that can hold an arbitrary number of ordered elements in it. Now, we could just create a list by consting things together in units until we have the appropriate number built, but it's much more convenient to think of a list as a basic structure, and here's more formally how we actually characterize it. A list is going to be a sequence of pairs with the following properties. The car part of a pair in the sequence holds an item, one of the things we're trying to collect together. The cooter part of the pair in the sequence holds a pointer to the rest of the list. And of course we need some way of telling when we're at the end of the list, so we have a special symbol called nil, which signals the empty list, or in particular that there are no more pairs and we're at the end of that structure. Another way of saying that is as follows. A list is a sequence of pairs ending in the empty list. Under that kind of definition, we actually see that lists are also closed. They're closed under the operation of const and cooter. In particular, if we have a sequence of pairs ending in the empty list, if we take a const of something onto a sequence of pairs ending in the empty list, what do we get? A new sequence of pairs ending in the empty list, therefore a list. So it's closed under the operation of const. It's also closed under the operation of cooter. If I have a sequence of pairs ending in the empty list, and I take the cooter of that, by my construction here, I get a slightly smaller sequence of pairs ending in the empty list. Therefore, it's a list. Therefore, I'm closed under the operation of cooter. This closure property means I can use lists anywhere I'd use primitive elements. So I can build up lists of lists, or lists of lists of lists. The only trick is, what happens if I try and take cooter of the empty list? Well, this is actually left undefined in many schemes. In some schemes, cooter of the empty list is itself the empty list in order to preserve this property of closure. In other schemes, taking cooter of an empty list will give you an error, saying you're trying to take apart a structure that doesn't have pieces. Nonetheless, we see we have a new conventional interface, a list, as a sequence of ordered items, which we're going to construct out of pairs. To visualize this, we use the following little notation. A const pair is represented as a pair of boxes glued together. The first box holds a pointer to the value of the first expression supplied to const. The second box holds a pointer to the value of the second expression supplied by const. And the whole box has a pointer into it, because that pointer is what's returned by evaluating the const. It gives us a pointer to the pair itself. A list then just consists of a sequence of const boxes. So in fact we see now the very nice structure of it. The car element of each box in this sequence points to the element of the list in turn, so it's an ordered sequence of things. And the cooter box of each box points to the next part of the list. So the cooters point to the rest of the list, including at the very end a special symbol for the empty list, which is that slash through the last box. This gives a nice way to visualize a list. It's kind of like a skeleton. The cooter pointers create the spine of this structure, and they point along in a line. Hanging off of each of them in the car spot are the ribs, which contain the elements of the list. And again, notice how the sequence is preserved. Also notice how this nicely indicates the closure property of lists. If I take the cooter element of any of these boxes in turn, it points to another list, a smaller one, that ends in the special symbol of the empty list. Therefore, that property of closure is nicely preserved over the operation of cooter. To check if something is a list, we have two things. First, we have a special predicate to check if something's the empty list. It's called null question mark. It takes an object of any type and returns true if that object is actually the empty list, or the special symbol nil. Otherwise, it returns false. To check if a structure is a list, we can just use pair question mark to check to see if it points to the beginning of a structure built out of conses. Although technically, we really should be careful and check that the last element is the special symbol, the empty list. Since we've built lists out of const pairs, we could use car and cooter to get out the pieces. But just for today, we're going to be really careful. We're going to separate out the operations on lists from the operations on pairs, and we'll create different constructors and selectors for a list. We'll let first get out the first element of a list. We'll define rest to be the thing that gets out the rest of the list other than the first element. And we'll define adjoin to be the operation of gluing something onto a list. And note, by the way, that these abstractions nicely inherit closure properties from the underlying abstractions of const, car, and cooter. Now, the key point behind defining a new kind of data abstraction or data structure is that it ought to make certain kinds of operations easy. And so we expect to see a standard set of procedures associated with each data structure. That's going to hold true with lists as well. In fact, one of the common patterns we should see associated with lists are procedures for creating them out of other kinds of data. So here's a simple little procedure that'll do it. It generates an interval of integers or numbers from a starting point to an ending point. And notice the nice little structure. It's a recursive call that basically says count up from the from point to the to point, generating new lists as we go along. And in particular, look at the recursive call. It says adjoin or glue the value of from, which is an integer, onto whatever I get by generating another list from 1 plus from up to 2. And how do I stop? Well, when my counter goes past 2, I'm done, and I'll simply return the empty list, or that special symbol nil. So here's a little procedure that uses the data abstraction to glue things together. And notice how that constructor is nicely used to put something on front of the other pieces. Also notice how it's building on a contract. If enumerate interval works well for small size problems, that is, if it generates a list, then the adjoin operation is guaranteed to give me a new list out because it glues something onto the front of a list, which I know by closure generates a list. And therefore, by inductive reasoning, enumerate interval will generate a list for me. To check this out, let's just use our substitution model. Here are the first few steps where I've abbreviated enumerate interval to EI just for space reasons. So if I enumerate the interval from 2 to 4, substituting into the body gets me that if expression. I evaluate the predicate, it's false, so I know as a consequence that I'm going to replace the entire if expression with the alternative clause. So evaluating enumerate interval from 2 to 4 reduces to adjoining 2 onto evaluate an interval from 3 to 4. Now remember, we first must get the values of all the sub-expressions before we can do any work, so we have to go off and get EI of 3, 4. And by the reasoning we just did, that reduces to another adjoin of 3 onto another call to enumerate interval from 4 to 4. Notice the deferred operations that are stacking up here. We expand another level and we get another adjoin pulled out and enumerate interval from 5 to 4. This time when we evaluate that innermost expression, the if clause is going to have a predicate that returns false. And in that case, we return the value of the overall expression as a nil. Again, notice the nice recursive buildup of deferred operations here. We've not created any pairs yet. We've simply deferred a bunch of creations of pairs until we've gotten down to this base case. Now we're ready to evaluate adjoin of 4 onto nil, and that creates a const pair. So just to show it here, I've actually drawn in the const pair. Notice how it has the structure of 4 and an empty list. The pointer to the pair is what's actually returned by this adjoin, and that reduces this expression to a simpler one. Now I'm ready to evaluate the next expression in this compound expression, which is the adjoin of 3 onto that structure. And that, of course, consts as another pair onto that structure, with 3 as the car, and the cooter pointing to the rest of the structure. And evaluating one more step glues the last pair onto that structure, and the value returned by the entire thing is printed out as the list open paren 2, 3, 4 close paren. So there's my list that I've generated. Notice the deferred operations, notice the order in which the things are constructed, and notice how const returns the pointer to the pair that can be used by the next call to adjoin. If we have procedures that can generate lists, or const them up, as we say, out of other pieces, we also expect to see procedures that can walk their way down a list, known as cootering down the list, either to find some value or to create a new list out of that structure. So here's a simple example and a very handy one. ListRef. Its goal is to pull out the nth element of the list, where by convention we use 0 to point to the first element of the list. Notice the nice structure of ListRef. It says if n is equal to 0, I'm going to get the first element out of the list. Otherwise, I'm going to rely on the closure property of lists, namely rest of list is itself a list, to do ListRef of one less thing. So by the closure property, I can recursively walk my way down the list, counting down till I find the point I want to, and I'm guaranteed to find the right thing. Unless, of course, I try and reference something beyond the end of the list, in which case I'm going to get an error. For example, if Joe is this simple list that we created previously, then ListRef of Joe and 1 will say, is n equal to 0? No. So take the cooter of Joe, which grabs the pointer that starts with the pair with 3 in the first element, and does ListRef on that list with n set to 0. In this case, when ListRef is run recursively, it says is n equal to 0? It is, and it returns the value 3. So ListRef basically recursively walks its way down a list, relying on the closure property of lists under constant cooter, until it finds the right place and returns the element hanging off the car pointer. I can, of course, do other things as I walk my way down a list. Another very handy procedure is length. It tells us how many elements there are in the list, or how long the spine of that skeleton is. And it does it with the same recursive property. If I have an empty list, the length is 0. Otherwise, the length of a list is 1 plus whatever I get by getting the length of the rest of the list, or the things hanging off of the cooter. By the closure property, if LST is a list, rest of list is also a list, and therefore I can apply length to it and get out the value of that answer. So again, I've broken this down into simpler versions of the same problem using my recursive property. In fact, this is a common kind of effect. Notice how the procedures we're building have a form or structure that tends to mimic the form or structure of the data abstraction. Lists are sequences of elements, so procedures to manipulate lists tend to be recursively things that walk down that sequence of elements, using selectors to pull out the right pieces. So let's put those two ideas together. Let's think about how we might cooter down one list while consing up a new list as the output of that process. Here's the simplest possible version of it. Suppose I want to make a copy of a list. Well, notice the form. If my input argument, LST, is empty, that is, if it's null, then I'll just return an empty list, making a copy of it simple. If not, the property of copying my input list consists of making a copy of the first element and putting it on the front of whatever I get by copying the rest of the list. Notice how I'm nicely relying on the data abstraction here. First is guaranteed to get me out the first element of the thing I'm copying. Rest by closure is guaranteed to get me out the rest of the list. Copy, by induction, can run on that smaller problem and will be guaranteed to return me a list, so that adjoining first onto that is guaranteed to give me a list as output. Therefore, copy is guaranteed to take a list in and give me a list back out. And by what we just saw, it will give it back out in exactly the order we put it in. Well, copying's pretty boring, doesn't make a lot of sense, but here's how we can use that idea. Suppose we want to take two lists and glue them together, append one onto the end. For example, appending the list 1, 2 and the list 3 together should give me a new list 1, 2, 3, 4 in that order. Again, the sequence or order is preserved. How could I build such a procedure? Well, I can take the thing I just did. I can use the strategy of copying the first list onto the second list, or putting it on the front of that list. So here's a very handy and useful procedure for two lists. Append is going to make a copy of the first list and add it to the front of the second list. And notice how it does it. It says, if I have an empty first list, then I have nothing to put on the front, so the base case here is simply to return the value of the second list, a pointer to that list. Otherwise, just as I did in the copy case, I make a copy of the first element of the first list and put it on the front of whatever I get by appending the rest of the first list onto the second list. There's that nice recursive form that nicely mimics the structure of the data abstraction and allows me to take advantage of the closure properties to guarantee that the program does the right thing. So again, we see procedures that manipulate list structure and generate list structure back out. They all rely on using the selectors and constructors to get out the pieces of the lists and to glue new things together to make new lists. So now we can put these ideas to work in handling more complex structures. Let's group together a set of points using a list. Then we can easily write a procedure to stretch the entire group by building on the wonderfully recursive nature of the list. Here it is. Note how we subdivide the problem of stretching a group into the operation of stretching a point, using the procedure appropriate for points, and then adding that to the result we would get by stretching the rest of the group. Because of the recursive nature of a list, we know that the rest of a list is a list. So we can use induction to conclude that stretch group applied to a smaller collection will return a new group, and thus adjoining the new element to the front of this will give us back a group. And if we want to find the midpoint or centroid of a group, we can put together the pieces we built earlier, as shown here. Add X and add Y have a structure very similar to our earlier examples. They simply cutter down the list, gathering up information as they go into a set of deferred operations, in this case deferred additions. Each of these will get the sum of the X and Y values of all the points in a group. To find the midpoint, we need to get the average X and Y value, so we need to know how many elements are in the group, and we get that using length. We can combine this information to create a new point at the middle of the group. Note the new form let. You can find the details in the textbook, but it suffices to think of this as an expression in which each of the names in the first set of expressions, X sum, Y sum, and how many, are bound to the values of the expressions following those names. Then, within the confines of the let expression, those names are simply local names for those values, and are substituted for just as we would in the standard substitution model. So to summarize, we have seen that languages often provide conventional ways of grouping data elements into structures, here either in pairs or as arbitrarily long collections. Associated with these conventional structures are methods for operating on them, and these procedures often have a form that mimics the structure. For example, in procedures that convert lists into lists, we see that the recursive step usually involves using the selectors to get out the parts of the list, operating on each, and then using the constructor to reassemble the parts into a list. This form means that the same inductive proofs we used to reason about our recursive procedures will also apply here. We can often deduce properties of our procedures and their associated data structures by relying on the fact that inductively the procedure operates correctly on smaller sized data structures. So let's step back and examine what we've built so far. We've basically built a hierarchy of data abstractions, each of which is constructed out of simpler ones. At the bottom are pairs, where we have a basic contract from Scheme about how const, char, and coder interact as data abstractions. On top of that, we have built lists, but where the user can take advantage of the fact that lists are also pairs. In fact, we do this directly by using char and coder as our selectors for lists. On top of that, we've just built groups, but again, the user can take advantage of the knowledge that groups are constructed as lists of lists, but where she's shielded from the fact that lists are implemented as pairs. In essence, what we've done is we've built a set of abstraction barriers in which the implementation details of a data structure are only weakly separated from the use of those structures. This means that we rely on the user showing discipline in applying procedures. And sometimes we're going to be much better off imposing strong abstraction barriers between the details of a data structure's implementation and its contract for usage. Or said another way, we've tried to separate out different kinds of structures so that we have conventions for helping us think about those structures individually. But we've allowed the user to cross over the barrier between those structures to get at the implementation of the structure below it. What happens if we decide to make those abstraction barriers much, much stronger, to really separate out the internal implementation of a data structure from the people that use it? This then leads us to the notion of a really rigorous data abstraction. And here, shown for pairs, are the kinds of things we expect to see in such a data abstraction. We'll have a constructor that glues the pieces together. It's going to have a contract between the types of the input and the type of the output, shown here. We'll have a set of accessors or selectors to get the pieces back out. And most importantly, we'll have a contract between the constructor and the selectors, so that whatever we glue together with the constructor, we can get back apart by using the appropriate selectors. Notice that this contract says nothing about how the abstractions are actually built. It simply specifies the interrelated behavior. We'll have some operations, standard operations on these data abstractions. For the case of pairs, we have pair question mark that tells us whether something is a pair or not. All of this is separated by what we're going to call an abstraction barrier. Think of it as a wall. Across this wall, very little can pass, and it separates out the use of the abstraction, constructing things, accessing things, the contract between them, operations on them. It separates all of that out from the actual representation and implementation of pairs. This means that any user living above that barrier can use the operation specified up there and basically freely manipulate the abstraction to get out pieces and construct new kinds of things. This user knows nothing about what's below the barrier and the actual details by which the constructor and selectors are implemented, nor how the contract is enforced between them. Okay, let's drive this point home with a slightly more extended example. And remember, the point we're trying to drive home here is this idea of separating out the details of implementation of a data abstraction from the use of the abstraction. We're going to put this very solid barrier between the two, and we're going to see why having that barrier, in fact, makes it much easier for us to create useful systems. The example we're going to use is rational numbers and simple arithmetic operations on rational numbers. I'll remind you that a rational number is just a ratio of two numbers, a numerator over a denominator. For convenience, we'll make them both integers, although they don't have to be. Associated with rationals, we have operations. We can add them together, we can multiply them, and the rules for that are shown in the next two lines. Notice that we're really cheating here. In fact, I've put the plus sign and the star sign on the left in red to distinguish that these are operations on rationals. And in fact, the rules, in essence, say how to decompose a rational operation into simpler operations. The things on the right-hand side of the equal signs are just normal integer multiplications and additions, and then the construction of the ratio, which is what that division sign is showing. Now, let's see how we can use the idea of rational numbers to build a data abstraction and use it. First, here's our data abstraction for rational numbers. And we know what we need here. We need a constructor. We'll just call it makeRat. It's going to take two integers in and produce for us one of these rational numbers. We'll need some accessors or selectors, numer and denom we'll call them. They should get out the pieces. Notice the type takes one of these rational structures in and gives us back an integer. And most importantly, what's the contract? Well, what we'd expect. We can use numer on the result of constructing a rational to get back out the first piece. And we can use denom on whatever we get out of constructing a rational to get back the second piece. We'll also have some operations on them. We'll have something that prints out rationals. We're going to have operations, as we saw, that can add rationals or multiply rationals together. And of course, we're going to separate all of this from the implementation. We should be able to have somebody hand us an implementation of rationals, constructors and selectors and operations, and we should in fact be able to build our own versions of operations just using those constructors and selectors, or build other operations on top of rationals that never need to know how rationals are actually built. We only rely on the contract between constructors and selectors. Now, let's think about actually building an implementation for rationals. Again, we've got all the first pieces of the contract. We're going to have constructors, accessors, or selectors, the contract between them, the other pieces. How would we actually make one of these things that satisfies the contract? Well, here's a simple implementation. A particular implementation of a rational would be to use const, char, and coulter. Our constructor makeRat would be built using const. Numer would therefore be char, and denom would be coulter. This seems obvious, but notice there's an important point here, one we're going to come back to. But the key point to stress is we can enforce the contract we require between makeRat, numer, and denom by inheriting that contract from const, char, and coulter. That is, since const, char, and coulter satisfy this contract, by the construction of makeRat, numer, and denom, we get the same behavior out. Nonetheless, by using makeRat, numer, and denom as our constructors and selectors, we've shielded the user from the internals of the fact it's built out of const, char, and coulter. And we'll see shortly why that's actually going to be important. In fact, here's exactly why it's important. Here's an alternative implementation for rationals. We could use makeRat as list, numer as char, and denom as cater. And I'll remind you that cater gets out the char of the coulter of the element it puts in. Does this satisfy the contract? Sure. Convince yourself by running a little example if you're not certain. Can a user tell which version we've built, the list version or the pair version? No. The whole point of the abstraction barrier is to shield the user from that kind of decision. Why would we want to have alternative representations? Well, we're going to see that shortly. Key point here is both of these implementations are valid. Both of them satisfy the contract. From the user's perspective, that's all that matters. For example, here's one of the operations we'd like to have on rational, something that prints out the value of the rational. And in fact, it'll use our internal scheme procedures of display to show the parts of the rational with that slash sign between them. Notice the type, takes in rat and doesn't say what it's going to return as type because it's just doing display. Most importantly, can this procedure tell which implementation of numer and denom we're using? And the answer, of course, is no. All we're using is selecting out those pieces. So we've separated out the use from the implementation details. What about my other two operations? Well, I can build those, and these have a form that's important to look at. Let's look at the first one, adding two rationals. Type says take in two rationals as input and give us back a rational as output. It's important that when we add two rationals, we get back a rational. What does this say to do? Well, notice the pieces. We first use the selectors to pull those data structures apart. numer of x, denom of y, numer of y, denom of x. Those selectors are getting out the pieces. We've now reduced this to simpler things, to integers, so we can apply integer operations to them, the multiplications and the addition. Same thing with the denominator. And then having done those operations, we glue the whole thing back together again with makerat. This is an important and common process. To build an operation on a data abstraction, we will tend to take that data abstraction, use the selectors to get out the pieces, reduce the computation to simpler operations on simpler pieces, do some work, and then glue back together the structures that we actually need. Also, notice how the types help us here. For example, what's a rational? It's something that's glued together with the constructor. If I apply numer to it, remember what my contract said. Numer takes in a rational and gives me back an integer. Similarly with denom. Therefore, I'm guaranteed in the first line of plusrat to get out two integers, so I know I can do the right kinds of work. I'm also guaranteed when I have that work done to have two integers back, so that I'm passing those into makerat. What was the contract for makerat? It took two integers in and constructed a rational. So by the type argument, I can see that my contract really is satisfied here. Okay, so let's use our little system. Let's create a couple of rationals. Makerat of 1 over 2 we'll call 1/2, because that's what it is. Makerat of 3 over 4 we'll call 3/4, because that's what it is. And we can now create a new rational. We'll define it to be new by using our operation for adding rationals, plusrat, to those two pieces. And we've just seen how to build it. We know this is going to go off, pull the things apart, do some arithmetic computations, glue them back together, and new will be a rational. Well, this sounds pretty straightforward. Now, what happens if we look at the pieces of new? We say, what's the numer of new? We get out 10. What's the denominator of new? We get out 8. Wait a minute. Shouldn't this be 5/4? We add a half to 3/4, we ought to get 5/4, but we get 10/8. So if you like, it got the right answer, but not the correct answer. And the reason is quite simple. Go back and look at what we said to do for the arithmetic operations. We're just taking the cross products of the numerators and the denominators. In fact, it's done the right computation. It just didn't give us what we expected. And in fact, that's exactly the point of this whole little exercise. Having seen that we can build rationals, having seen we've got opportunities for different implementations, and we should be able to shield the user of rationals from the implementation of rationals, let's think about what we could do to fix this problem. And what's the problem? We're not, quote, rationalizing the whole thing, or in particular, we're not reducing the rationals we compute to simplest possible terms. How do we fix it? Well, the easiest thing is to simply find the greatest common divisor of the numerator and denominator and divide both portions by that to make something smaller, to reduce it down to the smallest possible forms. Well, to do that, we'll just use GCD, greatest common divisor. Here's a little implementation of it. It's a simple little recursive call that will compute the greatest common divisor of A and B. You can check it out for yourself to convince yourself it does the right thing. Now we can use that to make better rationals. And here we have a choice. The first strategy says, let's remove the common factors whenever we actually access numer and denom. That is, we'll make the rationals the normal way, but when somebody asks for a part, we'll actually reduce it then. So here's a new implementation. Makerat looks just as before. It's constructing them together. But numer and denom will first compute the GCD of the parts, the car and the quitter, the way we glued it together, and then will give us back out the right answer, that is, the first element or the second element, respectively, divided by that greatest common divisor. This will, in fact, fix our previous problem. Now, when we add 1/2 to 3/4 and we go off and get numer or denom, we'll get back the right answer, which is 5/4. Also notice that since every operation we're building on rationals uses the selectors, it means that every other operation still will work correctly. All we have to change is numer and denom. Every operation built on top of that runs as before, but now inherits the correct behavior. This is exactly the reason why we separate out the use of an abstraction from the implementation of the abstraction. The selectors and constructors are basically the only procedures that can cross over that barrier. And as long as we make a consistent contract between them, use above will still work correctly. And to drive that point home, here's another way of making rational rationals. Now the strategy could be to remove the common factors when we actually create the rational number. In this case, numer and denom will behave as before, the car and quitter of something glued together, but now when we construct the rational, that is, when we call makerat, we'll compute the GCD of the two inputs and construct something that already takes those factors out. As before, the contract still works. Anything that was relying on numer, denom, and makerat still works. We have not had to change any of that code, but we've inherited the new behavior. Why would we have alternatives? Well, it depends on efficiency. If we're going to be using rationals a lot, we might want to do the rationalization when we construct. That way saving the computational cost in numer and denom. If we're using the opposite direction, we could take the alternative choice. To finish making this point, think about what would happen if we didn't put in the data abstraction between numer, denom, makerat, const_char, and quitter. For example, here's our version of plusrat that we had before. Let's suppose instead of nicely separating out the data abstraction from its use, we had implemented it directly in char and quitter. Well, here's that implementation. Looks just like before. I've just stripped away this silly abstraction and just put in the raw const_char and quitter. Everything looks just as before. But now we decide that we need to deal with this GCD issue. We've got to factor out that thing. Look at what we have to do to change plusrat. We've got to go in and actually get out the new version of numer and denominator by figuring out what are the right pieces to pull together, getting the GCD, and doing a lot of work. It's not just the amount of work that matters, it's the fact that this is very hard code to follow. How do we know what are the right places to match? What is the char corresponding to? How do we be certain that we've actually done the right pieces in all of this? The point is that we have here what's known as a big abstraction violation. That is, by mixing the implementation details with the use, by not strongly separating out the use of the abstraction from the actual implementation details, we've invited difficulties. We've invited the opportunity to have confusions as we go in to change those abstractions. We can't guarantee we've made the right changes, nor that we've made them in all the right places. In particular, not only would we have to change plusrat, we'd have to go change multiplyrat and any other operation that uses rationals to make sure that they do this work. In the previous case, we simply changed the selectors and we got the performance we wanted. So the overall point is, when we build data abstractions, we'll separate the use of that abstraction from the details of how we build it. That separation puts in clean boundaries that allow us to think about the uses of the objects without being confused by their details, and also allows us to cleanly, alternately create new implementations of those abstractions, creating new behaviors that are automatically inherited by procedures that simply rely on the abstraction themselves.